Hi, in this presentation we're looking at motion of connected bodies. And what is motion of connected bodies? Well, a quick Google search tells me that it is when two bodies are connected to each other and move together, or when these two connected bodies are move in a connected way, so they're moved together. And here are some examples of how these bodies are connected. So this is a simple example of connected bodies without friction. Uh, Calculate resultant force in the cable of the lift if the lift has a mass of 2000 kg and it is accelerated at 0.9 meter per second square. So A is going upward and B going downward. And so it's simply a pulley system. So we would have A here as the lift and B is the counterweight. So we need to figure it out what's the force needed to pull A up or let it down at a certain accelerated speed. So A, for the lift to accelerate upward, the force pulling must be greater than the weight of the lift. So we have the net force here equal mass time acceleration, but net force is also equal to the tension minus the weight. So the tension must be greater than the weight to pull the lift up. And here we rearrange the equation and solve for the tension, which is 21 kilonewton. And for going downward, the force holding the tension needs to be lower than the weight of the lift. So in the net force here, we have minus T plus mg. So the tension should be lower than the weight of the lift to let it down gently. And we rearrange it and we get 17 kilonewton. So if you calculate for the weight of the lift 2000 times 9.81, you would get 19,620. So if tension is higher than that, it would if the tension is higher than that weight, it's going to go up, and if it's lower, it would go down. Here we have a more standard example of a mass of 8 kg connected to a mass of 6 kg by an inelastic cord, and that passed over a frictionless pulley. When the 6 kg mass is released from rest, it's accelerated downward. Now calculate the acceleration of the system if the coefficient of friction between the 8 kg mass and the surface is 0.29. In this example, we ignore the elasticity of the cord and the friction of the pulley. So let's look at some free body diagram. So we have the 8 kg mass on the left and 6 kg on the right. It's always nice to have those around. It would help keep track of the calculation. So let's look at the 8 kg mass. So here we have the friction, where friction equals this bit here would be the normal force times the coefficient of friction. So the normal force here, this bit, it would be mg cosine 25 times the mu, which we know and that gives us 20.63 Newton of friction. Now, the net force of the system would equal to ma. Now, but the net force of this body is the tension minus the weight here minus the friction, which we just got, which we calculated earlier, and that equal to ma. And when we put all the known variable in there, we can simplify it to this equation here, which has two unknown variable, tension and acceleration, and that's as far we can go. So we're going to save that for later. Now, the 6 kilogram mass. Now, the 6 kilogram mass can only accelerate, by which it means go down, if the weight of the 6 kilogram is greater than the tension. So, tension plus, so negative tension plus the weight equal ma, and we just simplify that, and we got another equation which we can't solve. So we add equation 1 and 2 together, and we simplify it. Tension minus tension, so there's only one variable left, which is a, and we solve for a here, 0.362 meter per second square. And if you substitute it back into one of these equations, you would get the value of tension. Alright, last example. Here we have two bodies, one on top of the other. So we got the 20 kilogram on the top, and it is tied to the wall to keep it stationary, while the 30 kilogram block is being pulled by a force at 30-degree angle. Now let's draw the free body diagram. Yeah. So we see that we have two frictions, one between the blocks, or the bodies, one between the bodies, and another one between the bodies combined and the surface, the horizontal surface. And here, W1 and W2. W1 is the weight of the block on the top, and W2 is the combined weight of the top and bottom block together. Now, these two, N1 and N2, are reaction force or normal force, and they are the force that push back to the weight. So they're equal and opposite to the weight of the blocks. So N1 is normal force of the top block, and N2 is the normal force of the top and bottom blocks combined. And here is the weight of the force being that's pulling the bottom block out, and we got the vertical and horizontal component. Now we were given mu1 and mu2. Mu1 would be the coefficient between the two bodies, and mu2 is the coefficient between the combined bodies and the surface, this horizontal surface. And let's first consider the top block. So let's find the friction, since we know the value, the friction between the two blocks together. So you got mu1 0.25 and n1, which is the weight of the top block. So we got the mass times the gravity, and we got friction of 49 Newton. Now consider the 30 kilogram block, the bottom block. So we got a sum of vertical force. We have here P sine 30, which is the vertical component of the force pulling, and N2, the normal force of the ground pushing up against the combined body, minus the W2 here, which is the combined weight 20 and 30 together, times the gravitational acceleration, and all that simplify to N2 equal 490.5 minus 0.5 p. And that's all we can do for that. Now, the sum of horizontal force. We have the horizontal component of P here, and minus the friction 1 and friction 2. There you go, friction 1, friction 2. So friction 1 we already know right here, and friction 2 would be mu2, 0.3 right there, times N2, which is this one here. And from there we can rearrange and solve for P. And that is all to that. Thank you for watching. Like and subscribe. I'll see you next time.